Alright, so this question is an NMR question from Edexcel. It's a 6 marker, and a lot of people they hate NMR, which is why I'm doing this. A lot of people ask me to do an NMR question. So it's really important that you keep on practicing these and getting quicker at them just to make sure you secure those marks in the exam. And this I would say is quite an easy one relative to other exam boards and even other questions in Edexcel, to be honest, because it's just a simple compare and contrast. So it's not too bad. You should be able to do it if you've revised it enough, but we're going to go through it anyway. So have a go, pause the video, and I'll go through the answer in a bit. Okay, so the first thing that we notice, of course, is within Edexcel, whenever you have a compare and contrast, that's always making sure that you list out the similarities and the differences. So what I do, I literally bullet point my answers. So I do the similarities first, then the differences. And this is to make sure that I don't get waffly. I don't write in a big fat text that just takes me ages to write, and then it confuses me. It would confuse the examiners as well. So I would just kind of do a subheading of similarities, few bullet points, then differences, few bullet points. So that's how you should do it. So let's get into it then. So the first thing that I like to do with similarities, you can start off with differences as well, it doesn't matter. But the first thing you should notice that is very, very obvious is the benzene groups. So of course, both the compounds have a benzene group, which means that, of course, the hydrogens within that benzene group would produce a peak. And in A-level, we don't have to be able to explain this peak or the shifts or the splitting patterns, but we just need to know that benzene produces a peak because of its hydrogens. And because there's two benzene groups, we can say that the hydrogens within the benzene produce the same number of peaks with the same shift. So that's the first point. So both compounds contain aromatic hydrogens, aromatic meaning the benzene groups, which would have the same peaks/shifts. So that's the first point, easy mark. Now the second similarity is to do with the carbon-carbon. So if you notice, both of these groups or these compounds, they have a C double bond O, CH kind of group. So here is CH3, and then here is you've got the C double bond O, and then CH2, so CH again. So those two are the same groups as well. And if you look at the data booklet, that specific group would produce a peak between 1.7 and 3, or like 2.8 or something. Of course, it doesn't have to be exact. As long as the examiners know what you're talking about, you could just write the shifts as to what you think it would be. So that's the second one. So if I just get rid of these two, both compounds have a HCC double bond O groups, which would have shifts between 1.7 and 2.8. So in the mark scheme it said 3, but it doesn't really matter, to be honest. So those are all the similarities. So there might be more similarities in terms of the molecules themselves, but this question is to do with NMR only. So that would mean that all your points, you have to kind of link it to NMR. So now in terms of the differences, there are quite a few differences, some more obvious than others. So the first thing we would do in terms of differences is obviously count the number of hydrogen environments. So let's do that for phenylethanol. So with benzene, we have the first hydrogen environment here, and then we have an environment which relates to these two carbons, which is connected to hydrogens, and those hydrogens are in the same environment. So these two, here and here, they count as one environment. And then we could do the same with the ones above. So these two are also one environment. Now here, a lot of people make the mistake that this is also an environment because it contains a hydrogen, but it doesn't contain a hydrogen. There's no hydrogens on that carbon there, which means, of course, there can't be a hydrogen environment. So make sure you don't include that. Of course, here, there's no hydrogens connected, so that also can't be an environment. And then finally, this is the last environment, the CH3 group. And again, even though it's CH3, it's only one environment because all of these hydrogens are symmetrical to that carbon. So there's 4 environments in total in this phenylethanol. Now if you go to phenylethanol, the benzene would be the exact same. Again, making sure you don't include that. Then we have an environment here, CH2, and we also have an environment for the single H. So once you've kind of figured that out, that means that we have a difference in the number of environments. So we have 4 hydrogen environments in phenylethanol, and then 5 in phenylethanol. So that's clear. clearly the first difference. So phenethanone equals 4 hydrogen environments, the phenethanol equals 5. Now the next thing we could talk about is splitting. So let's kind of analyze the splitting in phenethanone. So actually I'm not going to get rid of that. I'll get rid of these 2 dots. I'll get rid of this 4 as well. So that's a 4 here. That's the first environment. So in terms of splitting here, so for this carbon, you might think that it would split into a quartet, but it doesn't split into anything because that carbon doesn't contain any hydrogen. So how can it split? So there's no splitting. But for these hydrogens here, there is splitting because there's a CH3 group and that CH3 contains hydrogens. So that can produce a peak. But what would the splitting be? Now, with splitting, we look at the carbon adjacent to the carbons that are attached to the hydrogens. So the adjacent carbon that is attached to the carbon which is connected to the hydrogens is this one here. So through that we use the n+1 rule. So you basically count the number of hydrogens on that carbon and then you add 1 to it, and that will determine if you have a singlet, doublet, triplet or quartet or whatever it goes up to, right? So here there's no hydrogens, but because of the n+1 rule, you count that as a singlet. So this here would produce a singlet. So that's the only kind of splitting we need to know. Of course, in terms of the benzene, there is splitting, but you don't need to be able to analyze that at A level. Now, the next thing is phenethanol, which is a bit more complicated. So we'll start off with this carbon. So again, we use the n+1 rule. So we look at the adjacent carbon, and we can see that that's attached to 2 hydrogens, which means you do 2 + 1 using the n+1 rule, and you'd get 3, so that'll be a triplet. So this carbon produces a triplet here. And then you have this carbon here. So again, same principle, you look at the carbon adjacent and you see how many hydrogens are attached. There's 1 hydrogen there, which means you add 1 using the n+1 rule to get a doublet. So this one would produce a doublet here. And remember, this carbon here isn't attached to any hydrogen, so you can just ignore that. So for phenethanone, we have 1 singlet, and then phenethanol, we have a ratio of 3 to 2, right? So we can write that as well. So phenethanone, 1 singlet, phenethanol, 1 doublet, and 1 triplet. Perfect. So that's the next point. So we've got 4 points now. We need 2 more. So another thing we can talk about is the peak area ratios, right? So again, this is slightly easier than splitting. All you do is you look at each environment and then you count how many hydrogens there are within that, and that will be your peak area. Again, we can ignore the benzene because that's too complicated. But for this, we see that there's 3 hydrogens, so it's simply just got a peak area of 3. And there's no more hydrogens in the compound, so that's it. We can just say that. With this, again, ignore the benzene. There's 2 carbons, each connected to hydrogens. So this would just be a peak area of 1 because there's 1 hydrogen, and this would be a peak area of 2. So we can write down that in phenethanone, there is a peak area of 3, and then in phenethanol, there's a ratio of 1 to 2 in terms of the peak area ratios. So peak area ratios, phenethanone has 1 peak ratio of 3, phenethanol has a peak area ratio of 1 to 2. Perfect, so we've got 1 more now to describe. And this one isn't as obvious, but it's still not too bad. So if you look at the data booklet and you see the group for aldehydes, you'd see that it's really far to the left. So it's got a shift of like 9 to 10 in between that, in that range. So of course with ethanone, you don't have that group. But with phenethanol, you do, because there is that aldehyde group here. So that's the last thing you mentioned. So ethanol, it has that group which shifts between 9 to 10 parts per million, and phenethanone doesn't. And notice how for every single point, I've compared the 2. So I've not just mentioned one of the compounds, I've directly mentioned 2 and stated the difference. That's where you get the marks. But yeah, that's everything. That's all the points that I can think of and that were in the mark scheme. So let me know if you have any more questions. If you have any questions regarding this question in particular, just drop me a message or leave a comment. And make sure obviously you like, follow, comment, share. And if you want any more kind of styles of NMR questions, just let me know.